Francesca is a PhD student here with us at the School of Meteorology. She works with Dr. Klein, and she worked with us on the Tracer campaign, which just wrapped up a few short weeks ago. Seems like a lifetime ago. But I'm sure she'll share some of her fun stories and lamentations as well from her time in Houston.
We wouldn't have the time for it.
Take it away, Francesca.
Yeah, thank you all for coming. This is my first in-person presentation as a grad student. Feels weird that my last in-person presentation was REU, kind of. So yeah, today we will be talking about the sea breeze and how it impacts the atmospheric boundary layer, specifically using UAS observations from the Tracer campaign. So we're going to start off with a refresher on what the atmospheric boundary layer is. So it's your lowest few kilometers of the atmosphere that is directly impacted by the Earth's surface. It is the medium which transports momentum and moisture and temperature. And instead of including our typical Stull diagram that us boundary layer scientists like to include when talking about it, we're going to just include some LiDAR data. So this was taken from just north of Houston, Texas. And we have a full day's worth of vertical velocity data and backscatter. So during the day, shortly after the sun rises, which is this dashed line, the Earth's surface begins to heat, and as a result, we have these convective bubbles and thermals rising and mixing. So we have a atmosphere that's dominated by updrafts and downdrafts, convectively mixing all of this moisture, heat, momentum. And then afterwards, the sun sets, and we have typically in clear skies, your temperature inversion sets in as the surface cools faster than the air above it, and in Houston, we had all of these pollutants that were trapped in the stable boundary layer, why we have this higher backscatter return. And then over top, we have a residual boundary layer, which is from the leftover convective daytime boundary layer. Let's get a little bit more complicated. So we'll take that canonical daytime boundary layer or convective boundary layer and juxtapose it with a marine boundary layer, which is a little bit different. It's a lot more shallow because we have cool air directly above the ocean surface. And so we get this stable internal boundary layer. Overall, the boundary layer heights are lower over the ocean, and your wind speeds are a little bit faster because your surface roughness is less intense. So we have all of these variations in your coastal boundary or your boundary layers over the land and over the water. So there are circulations which act to kind of equilibrate those differences. And kind of the most popular circulation that we all know and some of us love is the sea breeze circulation, which happens because I'm sure as many of you remember during either one of your first intro to meteorology classes, but the land heats up faster than the water. So you get rising motion and you get this pressure gradient force forming, which drives an onshore flow. You get rising motion because of convergence, as well as increase in your roughness length or surface roughness. You get rising motion, and then you get your return flow going back outshore, and it completes an entire little circulation. That's your broad mesoscale look at it. Within, you have this sea breeze front, which is typically a little bit taller than the rest of the driving gravity current. And because this is a sheared flow, you get these Kelvin-Helmholtz billows or instabilities that are changing how pollutants are transported and also moisture and momentum, adding a little bit of nuance to the sea breeze front, not just a blob of marine air that washes on shore. And with that, the sea breeze circulation itself impacts convective initiation because you have this kind of driving wedge that can force ascent. It's also bringing in moisture, but it's typically more stable. So how that impacts pre-existing convection, you have a stable air mass moving on shore. Is the lifting mechanism strong enough to overcome the stable layer? Also, with your aerosol distribution, there's kind of a twofold method. So you can have where there's enough lift and you have your aerosols being forced upwards, and you get this ventilation effect where it's taken back out to sea. Or you have a strong enough internal boundary layer where all of those aerosols or ozone concentrations are trapped very close to the surface, which obviously not great for health, human health overall. But A lot of these are very nuanced, and it depends on a variety of initial factors, as well as how strong, deep, how vertically deep and how horizontally deep your sea breeze is. And it doesn't help that we have this boundary layer data gap that I've talked about a few times here, that we're really missing data where your sea breeze circulation is most prevalent, and we're missing data in that layer of 10 to 1,000 meters, because above that, we have a pretty good look from radar and satellite. Below 10 meters, we have a good surface station network. But in that 10 to 1 kilometer range, the only thing that regularly passes through the boundary layer daily is radiosondes. But it's only twice a day, and they pass very quickly through that layer. So we're really missing, we're not capturing the spatial-temporal resolution of the boundary layer's evolution. On top of that, we have heterogeneities in our coastal boundary layer. It's not that clean picture like we saw on the first slide of coast and then water, where it's just a straight line. It would be way too easy. No, there are variabilities in your coastal topography, how your surface fluxes are on the land, and a variety of different things that impact how the boundary layers, or how your sea breeze forms. And moreover, your sea breeze in itself is complex depending on time of day, where you are, XYZ, so many variables falling into it. And this is traditionally modeled research. There have been a handful of campaigns, but really not capturing the small scale features that we need to fully understand the processes, which is where the Tracer Field campaign comes in. This field campaign took place in and around Houston, kind of backing all the way out into the Gulf of Mexico, with a handful of radars, profiling equipment, and different measurement tools to measure aerosol concentration distribution, to really understand, okay, how are aerosols impacting the convective life cycle? How are they affecting deep convection, radiative forcing, all with a area that is driven, has frequent sea breezes. So all of these kind of coming together across this map that we'll look at. And Houston was really chosen because it is incredibly industrial, and this urban sprawl is huge. So we have a whole bunch of very industrial particles coming in. Not to mention we have the Galveston Bay, which complicates things a little bit. And we have the Gulf of Mexico. So here is kind of the spread of observation equipment. And the last slide where we saw a bunch of different radars and scanning equipment are at this site. And then there are some scanning profilers or scanning radars at these other two red X's. We have thermodynamic and kinematic profilers. Clamps 1 up north of Houston, what that LiDAR imagery that I showed in the first slide. And then at the coastal center. And Michelle Spencer will be giving a talk in early December that will talk more about this. But for now, we're just going to focus on these two UAS sites down here closer to the coast, starting with the coastal center and the McCormick Reservoir. So the coastal center was co-located with Clamps. And we can see in this region, it is much closer to the bay, so it's going to get a lot of bay influence. It's also in a kind of low-grade urban sprawl, so you're still getting a little bit of the impacts from outflowing urban region, huge refinery over here. In comparison to McCormick, which was really just in the bayous, very rural, some refineries, but not as close to the one as we were in the coastal center. And McCormick was too far from the bay to really see those impacts as strongly. And you might be wondering, what even is a UAS and why do we care? So UAS are uncrewed aerial systems, and UAS in boundary layer research really go hand in hand because you have increased vertical resolution. You can dictate the ascent rate to customize how many data points you would need in your sample. They are highly reusable. This one in particular has over 26 flight hours on it, 255 flights, and it could still go, still going if it wanted to. With that, we can do flights every up to 15 minutes. We can also see the data in real time to make decisions. Overall, it has a small footprint. We're not adding any waste with each flight. And overall, it's not really impacting the environment too much like a crewed aircraft could. And mostly, it's just really cool. Thank you to Tony and Liz for figuring out how we could do that. And we weren't the only UAS out there. There was also the Raven from CU Boulder, which collected thermodynamic data and kinematic data, just like us, but also had the addition of an aerosol counter. So, and what I forgot to mention was our CopterSonde typically just does our vertical profiles versus the Raven, which is a fixed wing, so it's doing long kind of horizontal transects. And if it wants to do profiles, can do a helical structure to kind of replicate that. But we're really just going to be focusing on the CopterSonde, which holds all of its sensors in this scoop, so it is protected from too much insulation hitting the sensors. There are also duplicates, so there are 3 temperature and 3 humidity sensors, so we can average those duplicate sensors. The scoop is calibrated, so we're really getting high quality data, and we're backing the winds out by just how is the environment impacting the UAS itself. It is programmed to steer into the wind, which helps aspirate the sensors, which is a good thing. And also we back out the wind speed and direction by how much it's impacted by that. So kind of just sum things up on what we had accomplished over these 4 months. Each was a 2-week-long IOP, or intensive observation period, in June, July, August, and September. With that, we totaled over 546 flights, most of which were at the coastal center. Tried to get 50-50, off by a little bit, but 75% of flights reached our flight ceiling of 609 meters. And really, the only comparable thing we have at the moment to get those types of profiles are radiosondes, or one of the main comparable observation platforms are radiosondes. And if we wanted to do the same thing, it would have cost almost $110,000. So decent chunk of change when you can just send those pilots out there and they'll do it for you. So right in the air. But with this talk, I just want to talk about, since this is pretty initial, I've only been back from this campaign for a few weeks, it feels like, month and a half-ish. I'm going to provide an overview of the conditions that we sampled, see if we've captured the evolution in a complex coastal environment, and take a look at some initial case studies. So just the overall initial results, these are every data point collected throughout the campaign with height. And just to start off, it was hot. That's kind of a given, and humid, which everyone who came down with me can attest to. It was hot and humid. Winds were fairly light and tended to have a southerly component. But even though these winds tended to be southerly, there were some distinctive differences between the 2 locations. So just a refresher on where they were. The coastal center sites are these top row, and then at McCormick, the bottom row. And then this is different flight levels, so 200, 400, and 600 meters. And the first thing you might notice is there's just a lot more spread in your wind direction at the coastal center compared to the McCormick site. And even more so if you notice that these normalized distributions are much greater over McCormick. So you're really having a much stronger signal and more data points coming from the southerly flow compared to kind of all over the place at the coastal center. And this large easterly component really just has to do with its proximity to the bay. So you're getting some of that Bay Breeze influence at the coastal center more than the McCormick site. And you can also see that there's a little bit more variation in the wind speeds with height at the coastal center, which is most likely due to just the increased surface roughness at the coastal center compared to McCormick, which was pretty homogeneous and flat and close to the water. But overall, at McCormick, predominantly southerly flow. If the flow had really any strong magnitude, it was coming from the south or somewhat southwest. And next, we're just going to look at kind of the overall conditions. Starting off with, it was unseasonably dry, very dry and in drought-like conditions, severe to extreme drought-like conditions from June to August, with some relief to just moderate drought in September, which is kind of reflected in our number of convective days or convection days. So this table is completely subjective of me quantifying or qualifying days as sea breeze days, sea breeze with convection in parentheses, or just convection and near storm environments, or if we got rained out for a few flights. With this being a catch-all for, was the sea breeze there, or was it synoptically forced? Where you could see in June, not much convection at all, just one day with a very small pop-up thunderstorm, versus July and August, where there was a few more, but still 3 out of potential 14 days is not a huge sum. But we will first look at just a case from a sea breeze day. This is at the coastal center site. So we have a bay influence, and this was interesting because there was a really clear bay breeze to sea breeze transition, where these 4 panels are temperature, mixing ratio, potential temperature, and wind speed and direction. And kind of clearly in the wind speed, we can see this pick up increase in wind speeds, all kind of coming from initially from the east, around 1745, coupled with this increase in mixing ratio. And a slight decrease in your temperature, which is more obvious aloft than towards the surface. And then a little bit later on, 3.5-ish hours later, we get this more southerly dominating component, but we don't really see that same push of moisture. So we're going to look a little bit more zoomed in to each of those times, starting with the bay breeze. So these plots are timed profiles with starting at 17 UTC, and then incrementing initially at just the 30-minute step, and then after that, 15 minutes. So the darker colors are further on. And this bottom plot is, or bottom row, is just zoomed in up to 200 meters with a slightly augmented temperature scale to really see things a little bit better. And the most noticeable thing is this jump in dew point over a span of 15 minutes of about 2 or 3 degrees from 1730 to 1745. And with that, we have this variation in your temperature profile, which I find really interesting. We have this kind of temperature inversion, and then, you know, steep drop off where the air is being cooled. And then it might be a little bit hard to see, but this profile is actually followed by this profile, which is pretty well mixed. So you have that feature and then it's mixed out. And then it forms again as you have another push of marine air, and it's a little bit deeper across the layer. But you have a lot of this strong mixing. And then we can look at the sea breeze and kind of center our profiles around that moment. And you can see that overall, a lot more well mixed. There's a more gradual decrease in the temperature throughout the profile, but your small scale features and variability in that profile itself, they're not changing as rapidly. And these are actually progressing in 30-minute time steps as opposed to your 15. So not as quick of changes. And unfortunately, this case was not co-located with at this time, the Doppler LiDAR was not at the site. So we're going to take a look at a weaker bay breeze case so we can also look at some LiDAR data afterwards. This one's a little different. It's not as clean cut. You don't have that just like drastic, here's some winds and here's some higher moisture. It's a little bit fuzzier. There's a buildup in your easterly flow around just around 1800, and a slight increase in your mixing ratio. And then this case is kind of interesting because there is a moment in time for about an hour that a sea breeze tries to push in. You can kind of see it right here, this southerly flow below 200 meters, but it's a lot weaker and it really doesn't stick around. It eventually just washes out to a pure easterly. But you have this bay breeze push in, and now we're going to take a look at the profiles co-located with the vertical velocity data from clamps, which was just, let's say 10 meters, 10, 15, 20 meters away, not very far. But you can see that there are some little kinks in the profile mixed out. But as you jump 30 minutes, 15 minutes, you just see your turbulence is really dying out as that marine air mass has moved on shore. It's more stable. You're kind of damping out that vertical motion. So now we're going to kind of switch gears and look at a more convective case. And this day was had a stationary front kind of draped across the region, driving those cells kind of in a southward progression. And then you can kind of see right down here, the sea breeze front try and push in. So there's a little bit of collision between these cells moving out, moving towards the south, sea breeze front moving inland. And we have this variation in convection because of your sea breeze. So looking into this region, so before I lose my own train of thought, so we want to look at what happened to those cells once the sea breeze front hits those pre-existing cells that are trying to keep moving southward. And unfortunately, lightning risk, can't fly while there's lightning around, which was quite an issue for this particular day. So this radar loop is in between our flights, but we can see that the sea breeze really starts to push through. It's increasing in speed, all southerly, not a huge variation to your moisture content, but we can look at what was happening beforehand and then after your convection. So before, you can see through the winds, increasing southerlies with time, and really not a whole lot of variation in your thermodynamic or your temperature or your dew point profiles. But you do have some of these cells firing as your sea breeze is moving in. And afterwards, you have that convective or that more stable air mass moving in. We can look at afterwards. We have this almost stagnation in these convective cells. They've become very outflow dominant as we have that sea breeze really push through. And then afterwards, we have a temperature version and then an almost isothermal temperature profile with a little bit of variability in your dew point. But the flow near the surface was very weak. It was kind of stagnated between the various outflow directions, and sea breeze kind of washing out into a very light and variable winds at the surface, but remaining are these southerly flow wind vectors aloft. And obviously need to do a lot more investigation onto what exactly was happening, but also some cool things to look at in this post-convective environment. And with that, I don't have any hard-hitting conclusions. I've only had this data set for a few months, but I just want to point out that we've collected a really cool data set in a complex environment, and the other components in Tracer are really forming a very complementary and distinctive data set that I think will be incredibly useful for years to come. And we have been able to capture these fine scale features in the boundary layer. That was one of the first goals. And with that, we'll have my, the next steps are applying an objective method to determine the sea breeze days. Because like I said, how I was doing it before, very subjective. And then composite those ABL characteristics of the sea breeze days to understand really your time and height scales and the prominent features. And then my kind of next personal rabbit hole project is looking into what the pressure perturbations are telling us about the sea breeze strength, and depth and how that's really impacting the environment. And I have to acknowledge, first of all, the funding agency that made Tracer and my research at all possible, as well as Drs. Petra Klein, Liz Piller-Little, Heiste Bauer, and Tyler Bell for really helping, and all of their collaborators for helping me get to this point. Everyone who collected data in this sweltering heat, thank you. Some of you are here. I hope it wasn't too traumatizing to remember the days of Tracer. It's kind of a fever dream, but it was a time. The people who helped us fly, the owners at the two bayous, they brought us puppies. That was amazing. Super nice. University of Houston for letting us use the Coastal Center. Bucky and therefore Tony for buying Bucky for comic relief. And of course, my friends and family who keep me sane and allow me to even do research on a day-to-day basis. And really, most importantly, what everyone came here for. Jeez. And with that, I'll leave my concluding remarks. And I thank you so much. And I will answer any questions. Yes.
License data.
Yeah, I don't have a huge data assimilation background, but I know that it would be incredibly valuable to include it. I know that there are people from the Escape campaign who are working on data assimilation, and I'm positive that there's someone in Tracer. I just don't exactly know who. It is possible that if I really keep digging at things, that I might look at how modeling or model comparisons to the observations. But data assimilation is not my strong suit, but I'm sure somebody else is working on it. Yeah.
Did you happen to notice that the on TV one oh,
I haven't looked into that. That could be really interesting. And I think with the clamps data and positioning of the profilers and more of a, ooh, where did my mouse go? How do I get out of the laser pointer? Okay, I won't go back. Triangulating the different LiDARs to figure out a more 2D field and getting Fortis2 would be really interesting. But yeah, I almost wonder if it's less conducive in that region, not because the convergence isn't enough because it's not at a perfect timing. It's almost like the Bay breeze kind of washes over with a little bit of a stable layer. And as your sea breeze pushes in, it's like, well, I'll fire elsewhere, deeper where there hasn't been this stable layer. Because just in the planning of where we were trying to fly, I noticed that there wasn't a lot of deep convection in that corridor. And by noticed, it was a clicking through days of radar and just not noticing that there was a lot of deep convection right in that area. But that would be really interesting to look into.
Question in the chat from Lynn Sharma. Do you notice any drastic differences between pre-sea breeze front and post-sea breeze front heat value?
I haven't looked into that. I would imagine there would be. I will definitely have to. It might be very variable based on how you calculate your cape. Surface-based is going to be a little bit different for your most unstable, but that would be something to be valuable to look into.
Another question from the chat, from Brian Green. With how quickly questions change during the sea breeze event, conditions change during the sea breeze event, does it look like the 15-minute cadence is fast enough to characterize these changes?
I guess it'd be hard to say if comparing it to a faster cadence, but I think so. We did go up to 7 minutes once, and I don't know if we were getting a whole lot of changes in that 7-minute period that we weren't in that 15. So hard to say how much faster and how much more we're getting out of faster profiles that don't exist. But comparing it to, say, the LiDAR data, which is VADs every 5 or 10 minutes. Can't remember off the top of my head. 10 minutes. 10 minutes. I wasn't seeing a lot of differences on that order in profile to profile around that time that weren't there in 15. So probably. And it?
Thank you, Chris.
Mhm.